So let's get started. Today we're going to cover three basic topics in fastener assembly. We're going to start with tightening strategies, what they are and why they're important. We're going to cover the effects of assembly tooling on bolted joints, how they impact the assembly process. And the third topic is going to be bolted joint audits. How do you audit a bolted joint once it's assembled? And we have some techniques that you may find interesting to do just that. So without further ado, let's start taking a look at tightening strategies. Now here's a list, and we're going to present this here, a list of tightening strategies. We'll start with torque control, just using torque to control the assembly process. We'll use torque angle as a tightening strategy. We'll talk a little bit about the turn of nut method, the torque angle to yield method, tension control, and direct tension indicators, or DTIs. And finally, we'll have a brief discussion about ultrasonics. So what is the importance of having a proper strategy? Well, we all know what happens when the wheel comes off the vehicle. Fastener gets stretched beyond its elastic limit when the bolt is over-tightened. It elongates the threads between the threads, strips the threads, parts can be crushed or damaged, and obviously you'll have an assembly failure. Now what happens when a bolt isn't tightened quite enough? You'll end up with insufficient clamp load. The assembly comes apart. The parts loosen and become damaged, even though perhaps the assembly is still held together somewhat. And of course, you still have assembly failure. So let's take a look at torque control. Just what do we mean by torque control? Well, this is where torque is applied manually, typically using a dial or beam torque wrench with influence controlled a lot by the operator, how the torque is applied, what rate the torque is applied, and so forth. Torque can be applied manually using a clip-type wrench, and that's a little more accurate, but it's still influenced by the operator. An operator who pulls on the wrench very slowly and deliberately will have a lot better control over the assembly process than someone that's kind of yanking it or pulling it real fast or awkwardly. And torque applied using a pneumatic or electric tool can remove much of that operator influence. But torque control is really only just applying energy to the fastener to tighten it. It's not doing anything toward determining what kind of clamp load we're producing. There's the turn of nut method, and this is kind of an old one that goes back to the old railroad days. This is used most often in structural bolting applications, not very often in automotive. And the idea is to tighten the joint to a snug point, perhaps as much as 60 to 75% of the yield strength. And a reference location will be marked on the part and the mating surface, such that the second mark is made at the desired angle of turn, and the nut or bolt is rotated until the mark matches that desired angle of turn. This was a method used up into the 50s and 60s and into the 70s, quite often in bolting railroad rails together, or construction projects, bolting steel cross members in a building. But it's not really suitable for parts that cannot exceed the yield point. It's not good for gasketed joints or joints that are subject to disassembly. The next method we could talk about is torque angle control. It's more sophisticated than simple turn of the nut, and it's more accurate than just torque only. And basically what it is that there is a tool shutoff at a specific angle of turn following a specified torque. So in other words, you torque to a certain snug point and then turn it so many degrees. Torque is used as a coarse adjustment, and we could say angle becomes then our fine adjustment. The threshold torque can be set high enough to negate any scatter resulting from joint alignment or inconsistencies. And one of the big advantages of a torque angle control method is that torque only says that the tool hit the mark of torque. Enough energy was applied to the fastener, hopefully to reach the desired clamp load. However, if you have stripped threads or you have a cross-threaded bolt, sure, you hit your torque mark, but you did not advance the fastener far enough to actually tighten the joint. And that gives you that nice green assurance when you use torque and angle, because you applied enough torque and you also displaced the fastener or rotated it sufficiently to reach your desired clamp point. There's a method called torque angle to yield. This minimizes the tension scatter and maximizes the clamp load. And this is a method where the fastener is tightened to a torque that achieves 60 to 80% of yield strength, and then is turned to the point where the part is taken right into the yield point. I use the photograph here of an engine being assembled because this method is used for many critical fasteners in powertrain, whether it's head bolts, connecting rod bolts, main cap bearings, and so forth. The fasteners that are used are specifically designed for this type of method, and they're commonly used with necked down fastener designs so that yielding occurs in the neck of the shank of the bolt rather than in the threads. And you want to note that normally threads will yield first, which can cause a change in thread pitch, which may be then able to prevent the part from being disassembled. So we want to make sure we keep that in mind. The next method is tension control. This utilizes a sophisticated control system that monitors torque versus angle or torque versus time. When the torque-angle relationship transitions from the linear relationship, in other words, when the amount of torque increases at a different rate than the angle of turn, that will indicate the onset of yield and the driving tool is shut off. This can accurately predict the load point on the joint to within 90% of the yield strength. It will also detect poor thread quality and cross-threading, similar to the torque angle method. It's well suited for critical assembly line applications due to the expense. The next method we're going to talk about is the direct tension indicator, or DTI. These are washers typically with raised projections that collapse when the desired tension is achieved, using pretty much the material properties of the fastener itself. There's a squirter type of DTI washer that has silicone or other material that's contained in a depression that will squirt out when the desired tension is achieved. This is often used in conjunction with feeler gauges to guarantee that the washers are properly flattened. Smart bolts have tension indicators built into the bolt head to indicate the bolt stretch. Sometimes we have also smart bolts, which have a tension indicator built into the bolt head that will indicate the amount of bolt stretch. The final method that we'll talk about here uses ultrasonic technology. This is a promising technology that uses ultrasonic elastomers to measure the bolt stretch. It works on the principle that the ultrasonic signal will take a predictable time to travel through the bolt and back. As the bolt stretches, that time interval will increase. Now, this method does require careful preparation and calibration of the fasteners. And there are possible errors when you're dealing with short grip lengths, long fasteners with small diameters, and when used with parts with alignment issues. But which strategy do you need to use? Well, in the context of a 20 or 25-minute seminar, it's difficult to tell you specifically which strategy to use, but we can offer some general guidelines. The selection of the tightening strategy should be determined by the volume of production, how many parts are you making and what kind of time interval. The criticality of the joint. Is this a critical joint that requires a highly sophisticated tightening strategy, or is this a non-critical fastener where if you tighten it so it's tight and it feels right, you're good to go? There's also the cost of investment. Is this not only a critical joint, but the cost of potential warranty, repair, or failure would be significant. And there's also the customer requirements. What does the customer require in terms of quality and bolted joint integrity? All of those factors will influence greatly what kind of tightening strategy you'll employ. The specifics of the tightening strategy, such as the snug torque, the torque or angle shutoff, tool speed, and so forth, should be determined through experimental testing. So now we're going to turn to the effects of assembly tooling on bolted joints, which is really shows you the importance of assembly tooling in your process. So tooling effects require that you use the proper tool, because the wrong tool can make or break joint integrity. Coordination of tool selection and tightening strategy is very important. Next, we'll look at the types of tools. And this is just a kind of a quick overview of different types of tools that are used. I'm sure there are tooling people that may be in attendance here today that could fill you in on some of the other specific types, but we're talking in general terms here. We'll start with pneumatic tooling. Pneumatic tooling may take the form of an impact driver, simply a torquing tool driven by pneumatic air pressure. It may be a direct drive air motor with a gearbox, such as the one that's shown here, or it could be an impulse tool, which is a pneumatic tool that's driven by pneumatic pressure, but uses a hydraulic cushion to shield the operator and the bolted joint somewhat from the harsh blows delivered by a pneumatic tool. There are stall tools simply pneumatic tools that run until the air pressure can no longer rotate the tool. There's air pressure sensing tools that will run until a specified air pressure is reached. And clutch tools, a torque shutoff that uses a mechanical clutch. Again, a pneumatic tool with a mechanical clutch. There are pneumatic tools with electric control that use some sort of an electronic device, such as a reaction torque transducer that's located in the middle of the tool that senses the reaction torque between the motor and the housing and will use that to shut off the air pressure. There are transducerized clutch tools that are much the same, that use a mechanical clutch to shut off the tool, but still monitor the amount of torque that's being applied to the fastener. There's a transducer-controlled pneumatic tool, and this is one that will use that reaction torque transducer to actually do the shutoff. There's electric tooling. Electric tools tend to be lighter in weight than air tools, and they typically will use a brushless DC electric motor. They're a little more expensive than pneumatic tools, in some cases a lot more expensive. But you don't have any oil contamination. You don't have any pneumatic air lines to maintain. They often feature significantly reduced noise and vibration. And then you have transducer-controlled electric tools that offer a higher level of performance and control and are capable of different torque outputs and tightening strategies. And of course, there's a lot of battery tools nowadays that offer portability and the performance of air tools without hoses or cables. Now let's look at some of the physics behind these tools, such as, let's say, a pneumatic impact wrench. We want to keep in mind that a pneumatic tool uses more or less a hammer and anvil principle to impart the energy to the fastener in short bursts. So these sharp hammer-like blows of air are attempting to pound the tool, work the tool in a rotary fashion. One of the problems with this type, though, is that there's little correlation between torque and tension. As the illustration attempts to show, you're basically putting a wrench on the end of onto the fastener and pounding it with a hammer, the hammer being the sharp pneumatic blows of air. The control of tension with an impact tool is negligible because all you're doing is applying torque through the impact of the tool and hoping that over some period of time you'll reach the optimal clamp load for your assembly. We've often thought in our end of the business that impact tools are really designed to remove rusty or stuck bolts. They probably should never be used in any kind of an assembly process for a critical fastener. Pneumatic drive tooling, such as impact tools or impulse tools, will produce this kind of an output. The graph here shows the input torque versus time of an impulse tool. And you'll notice that the line that passes through, it represents the amount of clamp load that was achieved. So if you look at any of these sharp hammer blows of torque, there's none of these singular torque values that really relate to the amount of clamp load. What actually relates to it more is the length of time. So within 5 seconds or 7.5 seconds, you've pretty much reached the maximum amount of clamp load you're going to achieve in this particular joint. Impulse tools are used often because they do use hydraulic fluid to soften the energy transfer process. And they do offer user-friendly ergonomics. Operators prefer them significantly over typical pneumatic impact tools. But the problem is there's very little torque tension correlation. Now, when we look at an air tool and we compare torque tension and RPM, well, the application of torque until the shutoff is typically pretty consistent. But one thing that can be noted is that the tool speed will slow as the fastener is tightened. And in a way, this can impact the accuracy of the torque shutoff due to the change in friction, because the speed of the application of torque is very critical in determining the state of friction in that joint. We discussed that last week during the initial segment. Now, when we look at a DC electric tool, yes, it has the same steady and consistent application of the torque to the shutoff point, but it also has a very consistent tool speed that ensures accurate friction calculations and accurate clamp load. One last thing I want to talk about in terms of tooling effects is tool speed. And this is very significant. Here we have a graph, and we're showing the same joint tightened at 2 different speeds. I'm going to spend a minute or two extra to talk about this. The customer came to us with an assembly issue. They were having loose fasteners and broken fasteners and over-tightened fasteners. And when they sent their parts in to be tested, we asked them what the tool speed was. And they told us, well, geez, we run that tool as fast as it will go, because this is a high volume production part, and we need to get these parts done, these assemblies done as fast as we can. Remember, that's one of the considerations when we talked about tightening strategies, was the volume of production and the cost pertaining to that. So they were trying to get their assemblies done as fast as they could, so they were running their tools at as high a speed as the tool could maintain. But as you can see here in the red graph, running that tool at 200 RPM, they were getting this serious stick-slip situation with their torque, where the coating, the E-coating on the part, would liquefy and then burn off. And as that fastener was tightened, it would screech like a banshee, as we started talking about. And it was very inconsistent, because the tool would shut off saying, well, I hit my point, I hit my shutoff point, I'm done. So we started looking at tool speed as a factor and convinced the customer to try to slow down the tool. And what we found is when we got down to a speed of about 25 RPM, all of a sudden they were getting a nice, smooth, even application of torque. And once they started doing that, all of a sudden their over-tightened fasteners and their loose fasteners disappeared, and they could cancel that 100% inspection of all of these fasteners at the end of the assembly line. So tool speed is very important. You can use high RPMs to run the fastener in prior to or up to the snug point, but to get to that final snug point and then turn to the final tightening spot, you definitely want to drop your RPM down. It's very important. Well, next, we're going to go to take a quick look at bolted joint audits. When you're determining joint integrity, it's important that you audit the joint in some way, because what you're doing when you tighten a bolt is pretty simple. You're applying force at a distance, you're producing tension in the bolt, that is, you're stretching the bolt, and you're then developing a clamp force or clamp load on the joint. So in order to ensure that that joint is going to withstand the working loads it will experience during its service cycle, it's important to audit the bolt tension or clamp load after the joint is tightened. So what are traditional audit methods? Well, we'll start with just monitoring the input torque, either using the installation equipment or using post-installation audits. Some of the problems with this is the input torque is largely influenced by friction in the threads and underhead regions, and input torque is strictly a measure of how much energy is transmitted to the joint, not how evenly the energy is distributed. Now, post-installation audits might use a method such as tightening the fastener an additional 5 to 10 degrees. So the operator, the quality operator, will apply torque until the fastener just begins to move that additional 5 or 10 degrees. The peak torque can then be monitored and recorded, such that if you looked at it graphically, you might be able to see what that initial point was where the fastener broke loose, where your torque was maybe at 5 degrees, where your torque was at perhaps 10 degrees. And you could get an idea at least of what your residual torque would be. However, this method is largely dependent on the operator. So as the operator is applying torque with the wrench, he has to be looking very closely and moving it very, very carefully to note right when that fastener begins to move. So the limitations of traditional audit methods are that you're really not verifying tension in the joint. You're not really taking friction into account, and you're only truly monitoring torque tool performance, not joint integrity. The actual residual torque is not measured specifically. It's only inferred by where the fastener begins to move. And the measured torque value is dependent on the person performing the audit. Now, there's a method that can be used called M-alpha, the M-alpha auditing method. And what this does is monitor joint tension using torque angle signature analysis. It correlates the angular displacement of the bolt to the stretch of the bolt. And it does so by generating what we call an M-alpha diagram. An M-alpha diagram being a straight line projection of the tangent to the torque angle plot, projected backward from the final elastic tightening point to zero torque. And we'll explain what that's all about coming up. So what is the M-alpha method? Well, let's define a couple of things. First thing is the elastic origin, the point at which the projected tangent line crosses the zero or prevailing torque level. That's where the tightening, the true tightening, the development of clamp load begins. There's clamp angle, which is the angle measured from that elastic origin to the final torque value. The clamp angle is directly proportional to tension in the joint. The one caveat here is that it's only valid in the elastic clamping zone of the tightening curve. That is the linear portion prior to yield. Once the fastener is taken into yield, the M-alpha auditing method will not be helpful. Now, how do we do an M-alpha audit? Well, first, you want to experimentally qualify a joint to create a tension-torque angle relationship. You want to find the torque angle, the torque tension, angle tension, and torque angle coefficients. So, for example, you want to see what the torque was at a given tension. You'd like to research your joint to determine what your clamp angle is. How many newtons per degree do you get? And the third thing is you want to see what your torque versus angle relationship is. And you can use coefficients, these coefficients, to monitor tension using the clamp angle from the elastic origin to the residual torque value. Well, how do we actually do a torque angle or M-alpha analysis? Well, first of all, the first step is to pick our points. So we're going to locate 2 points on the linear portion of the torque angle signature. The second step is we're going to project a line through those 2 points back to either the zero torque, or if we're using a prevailing torque lock nut type, to that prevailing torque level. Our third step is to locate the elastic origin, where the projected line intersects that zero prevailing torque level. This fourth step is to measure the angle of turn from the elastic origin to the final torque value to obtain the clamp angle. So if you know and have determined the angle tension coefficient, you can then very accurately confirm the amount of clamp load, such that in an example such as this, if we see when we audit the fastener that our clamp angle was 85 degrees, we will know, and because our angle tension coefficient came out to somewhere around 88 newtons per degree, or in this case, 88 pounds per degree, we could multiply our clamp angle, our audited clamp angle of 85 degrees by 88, and we would get about 7,500 pounds of clamp load, which would be our target. So again, it's determining what our elastic origin is and what our clamp angle is. And once we had verified what our angle tension coefficient is, that is, how many pounds or how many newtons of clamp load we received per degree of turn, elastic turn, then we can then simply apply torque to a tightened fastener, pick off our 2 points in that linear clamping zone where we advance the fastener, draw our line, and see what our clamp angle is. And there are electronic devices that are capable of doing this. It's a very handy way of verifying joint integrity. So in summary, for this afternoon, we talked a little bit about tightening strategies and how they have to be individualized for your specific application. For non-critical fasteners, You don't need to get too sophisticated. But if you have a critical fastener, or if you're having a joint that's giving you some kind of problem and you're having to troubleshoot it, you can always use a more advanced tightening strategy to better control your assembly operation. The tool type and speed can have a great effect on assembly integrity. Using a primitive pneumatic tool on a critical fastener is not recommended at all. And if running a tool at a higher rate of speed may not be as efficient, even though you may want to kick out a lot of assemblies, it can lead to some pretty disastrous consequences. Critical bolted joints should be audited during or after assembly to ensure proper assembly. And finally, the M-alpha bolted joint auditing process can help determine clamp load.